Hello everybody, I'm back again with another problem to talk about related to physics. Here we have a challenging problem, which I'm going to break it down and I'm going to show you a really nice geometrical way to try to understand what's going on. So here we have a problem. Cars A and B are traveling in adjacent lanes along a straight road. At time t equals 0, their positions and speeds are as shown in the diagram. If car A has a constant acceleration of 0.6 meters per second squared and car B has a constant deceleration of 0.46 meters per second squared, determine when A will overtake B. So determine when car A will overtake car B. So I want you to understand something. Whenever we want to determine when one object is going to overtake another object, what we're essentially doing is we are equating their positions. Okay, so right away we want to start off, and I made some illustrations here so we could understand it, what's going on. So I listed my knowns. I have car A at 13 meters per second and car B at 20 meters per second, and they're 30 meters apart. So that means as the problem begins, car B is already 30 meters ahead of car A. So if I graph this, there is something I want you to notice, that these problems don't actually relate to triangles. They are trapezoids. Okay, they are trapezoids, and that's really a key point. So if car A is traveling at 13 meters per second, that means at this point right here will have to be 13. So that's our 13 right here. And he's traveling and he's traveling and he's traveling. But notice something here. The acceleration here is constant. So if it's constant acceleration, our acceleration graph will have a horizontal line. Now look at car B. It has a deceleration, and as the problem begins, he's currently traveling at 20. But he's decelerating, so we know the line has a negative slope to it, and that's what we see illustrated right below it. This is a negative 0.46. Okay, and those are the graphs of these two problems. Now, let's begin the problem. So let's start with car A. So it resembles a trapezoid. So I'm going to begin by first, let's start with a trapezoid. Okay. So there's a lot of unknowns. And we're going to make this position A. Now, I want you to notice something here. In our acceleration graph, the area under the curve is equated to the change in the velocity. And our change in velocity is going to be equal to 0.6 t. Okay, 0.6 t. So I can write for my final velocity, I can make a relationship and say that my final velocity is equal to my initial plus my change. and my change is 0.6 t. So I'm going to replace VF with VI plus 0.6 t. And it also is very helpful if we start using brackets here, since we have some parentheses. So I want to clearly indicate that that is my final velocity. So my initial velocity for car A would be 13 plus 13 plus 0.6 t. This is going to be 26 plus 0.6 t. If I distribute now, so here's where the algebra comes in. I have 26t plus 0.6 t squared. Now I have 13t and 0.6. We're going to divide that by 2. And we end up with 0.3 t squared. And that is our complete position equation for car A. Okay. Now we want to look at car B. So here is our car A analysis. Now I want to look at car B analysis. And it's helpful to keep in mind the information. So what we want to do is we want to bring this information here down. And I want to keep a graph right here just so I can make sure that I have all my information correct. Now here, we're going to do the same exact thing, the same exact mathematical idea. I'm going to find a position equation. So I express the position x as a trapezoid. And right here is our delta v. And we also have delta v is a times t. So we get negative 0.46 t. Once again, let's see where we are. So here we have x equals 1/2 bracket vi plus parentheses. Our final velocity is initial plus delta v and the initial velocity given was 20. So that's going to be 20 minus a 0.46 t So here we have 40. And let's do a little simplifying here. So 1/2 times 40t minus 46t squared. So you get 20t minus, and now we're going to distribute the 1/2 to the negative 0.46, and we get minus 0.23 t squared. Now, remember that at position 0, car B had already gone 30 meters. So our total position for car B would be 20t minus 0.23 t squared plus 30. So we have our position for car B. And what do we do with all of this information? Now we have to equate the positions to get the time when they overtake each other. So I will go up here, and let's bring this information down. Here's our car A. And I'm going to equate this to car B. All right. Now, I'm going to bring everything over to the left side. So I'm going to have 13t plus 0.3t squared minus 20t plus 0.23t squared minus 30 equals 0. And now I'm going to simplify this and putting it in order of descending exponents. So I end up with 0.53 t squared minus 7t minus 30 equals 0. And here we have a quadratic. So by the quadratic formula, I'm going to first put down what A is 0.53, B is minus 7, and C is minus 30. So we'll have T equals negative B plus or minus the square root of B squared minus 4AC, all divided by 2A. And by the quadratic formula, you want to choose the positive answer. So you'll have time is equal to 10 over 53 times 35 plus minus the square root of 28.15. We choose the positive, so we're going to get t is approximately equal to 16.61 seconds. And that is the point where they overlap each other and continue going. So I want you to take this problem, read it over, make sure you understand the concepts and not just do the problem and look for an equation. If you just start out and just write down formulas and say, let me do the problem, without truly understanding the concepts and how we arrive at them, when we go to another problem that utilizes the same type of mathematical analysis, you won't understand it as clearly. By doing this problem in this matter, you truly understand the concepts. So thank y'all for listening. Check me out again for the next problem coming up. It's been another great day in thinking physics. Take care and have a nice time.